Okay, particle B of mass 5 kilograms is at rest on a smooth table. So 5 kilograms. A particle A of mass 2.5 moves on the table with a speed of 6 meters per second. So this is A, this is B. It's moving at 6 meters per second. And it collides directly with B. Of course, it's 2.5 kilograms. When they collide, the particles coalesce, and we need to find the speed of the combined particles after collision. So the principle we use for this question is that momentum is conserved in a collision. So momentum, you may remember, mass times velocity. So the mass times velocity of the objects before is equal to the mass times velocity of the objects after. So before we have, well, particle B is at rest. So it's 5 times the velocity of 0, which is just 0. That's its momentum. Plus the momentum of A, which is 2.5 times 6, is going to equal the momentum afterwards. Afterwards, the two masses combine, and so the 5 kilograms merges with the 2.5 kilograms and becomes 7.5 kilograms. And we want to find out what the velocity is, and that's the equation we solve. All right, so the velocity will equal 6 times 2.5, 2 6s are 12, half of 6 is 3, 12 plus 3 is 15, divided by the 7.5, and we have our answer, which is, of course, 2 meters per second. Find the loss of kinetic energy of the system due to the collision. All we have to do is find the kinetic energy before, the kinetic energy after, and see what the difference is, see what was lost. So the kinetic energy, hopefully you remember the formula, is a half of mv squared. So the kinetic energy before, if you don't have a velocity, you have no kinetic energy. So there is only one item which is moving, and that's particle A. And its kinetic energy is going to equal a half times 2.5 times 6 squared, which equals 45 joules. After, the kinetic energy is the same formula, half mv squared. And in this case, it's now going to be a half times 7.5 times the velocity, which we just found out, 2 squared, which equals 15 joules. So the K that's lost is what we had before minus what we have after, and that turns into 30 joules. A car of mass 1,400 kilograms moving along a straight horizontal road against a resistance of magnitude 350 newtons. Find in kilowatt the rate at which the engine of the car is working when it's traveling at a constant speed of 20 meters per second. Okay, so if it's traveling at a constant speed, that tells us a couple of things. It's not accelerating, and therefore all the forces must add to 0. We're told that there's a resistance force against the motion of 350 newtons, so my car is going right on the diagram. The driving force must therefore equal the 350 newtons, so that they cancel each other out and it travels at a constant velocity. We know that power is force times velocity, and so we know the force must be 350, and we know velocity is 20, and so power is pretty easy. 350 times 20 is 7,000 watts, though the question does tell us to give the answer in kilowatts, find in kilowatts. So the answer in this particular case is 7 kilowatts. And we're done. Find the acceleration of the car when its speed is 20 meters per second and the engine is working at 15 kilowatts. So hopefully we picked up that the engine power has increased. It was 7, now it's 15, which means we're expecting that it's going to be accelerating forwards. And of course, we use the same formulas. Power is force times velocity. The power is now 15 kilowatts, so don't forget to change it back to watts. We're going to change it to 15,000 watts, which is equal to the force times the velocity, which is 20. That tells us the forward force, or the driving force from the engine, is equal to 15,000 divided by 20, which equals 750 newtons. The resultant force is mass times acceleration, and that's going to equal the forward force, which is what we just worked out, minus the resistance. The mass of the car is 1,400 kilograms multiplied by the acceleration, I was going to write kilograms, is equal to the driving force minus the resistance. It was 350. And all we have to do is solve for acceleration. So for acceleration, we're going to have 750 minus 350 is 400. We divide it by 1,400, and it's a bad decimal. Let's keep it as a fraction. 2/7 meters per second squared. Question 3. Coplanar forces of magnitudes A, 12, 10, and P act on a point in the direction shown in the diagram. Systems in equilibrium, find P and theta. When it's in equilibrium, all of the forces must add to 0. So all we have to do is resolve horizontal components must add to 0, the vertical components must add to 0, and we would be done. So for horizontal components, the forces going left are P and 10. So we could say P cos theta plus 10 cos 45 has to equal the forces going right, which is 8 cos 30, and the last one is just 12 because it's just going right. So that's the horizontal forces. There's the two unknowns are in the P cos theta. It would be handy if they were on the same side and we work some of those values out, maybe at some point. For the vertical forces, the two forces going up are P and 8. So upwards it would be P sine theta plus 8 sine 30 has to equal the forces going down, which is 10 sine 45. And the 12 has no component going up or down. And so there are two equations that we have to solve. We have two unknowns, two equations. It should be able to solve it. When you look at that, you hopefully would go, oh, if I divide sine by cos, I get tan. So let's try and arrange it so we can work out a tan. And the p's would cancel when we divide. So let's start with the second equation, and we'll get P sine theta, just an easy rearranging, is equal to 10 sine 45 minus 8 sine 30, keeping exact values at the moment. And for the first equation, we can get P cos theta on its own by doing the same thing. Let's take the 12 out the front, plus 8 cos 30 minus 10 cos 45. Okay, so two equations. These are more helpful, these equations. Let's take equation 1 divided by equation 2, and that's going to be very helpful. Because P sine theta divided by P cos theta, the P's cancel to make 1. We get sine theta divided by cos theta, and that just gives us tan of theta equals something a little crazy, but we can manage it. Tan sine 45 minus 8 sine 30, all divided by 12 plus 8 cos 30 minus 10 cos 45. Okay, that's why we have calculators. So make sure your calculator is in degrees mode. Notice the angles they give us are in degrees. And we just can put that into the calculator, do the inverse tan of what we get, and we'll get the angle is approximately 14.5, rounded to 1 decimal place, 14.5 degrees. Right, to find P, we just use either equation 1 or 2. So let's use equation 1. We want to find P, so let's take the sine theta, divide it into the other side, and we will get tan sine 45 minus 8 sine 30 divided by what we just found out for theta, sine 14.5. All right, I'm not going to use 14.5, of course. I'm going to use the exact value so I get a more accurate answer. So P is equal to 12.248. All right, the front of the paper says give your answer to 3 significant figures. So we'll go 12.24, just stays as 12.2. That's the newtons, the force, and the angle, let's put our answers together, was 14.5 degrees. Finished. A particle P moves in a straight line. It starts from rest at point O on the line, and after time t leaving O, it has an acceleration, and there's an equation based on time, a equals 6t minus 18. All right, because acceleration is not constant, we're going to use integration and differentiation. We have functions of time. We integrate acceleration, you get velocity. You integrate velocity, you get displacement. And so we need to find the distance that P moves before it comes to rest. Notice that it starts at rest at point O, so when time is 0, it is at rest. So we can find the velocity by integrating the acceleration. The 6t, t would integrate to squared, and we divide 6 by 2, and we end up with 3t squared. And then we're going to subtract 18 t, and of course when we integrate you should always add a constant. In this case we know that it starts at rest, and so when time is 0, velocity is 0, which therefore c is going to be 0. If you look at the equation, if v is 0 and t is 0, well, c has to be 0 as well. So you should always check just in case it doesn't work out like that. But for us, the equation is 3t squared minus 18t. Okay, we have to find, when it comes to instantaneous rest, it starts at rest. We want to find the next time is at rest. And so that's when the velocity is 0. When the velocity is 0, we get 3t squared minus 18t equals 0. To solve any quadratic, we try and factorize. Let's take out 3t, and we're just going to be left with t minus 6 is 0. So the two answers, of course, we knew that 0 was one of them, and t is 6 seconds. So 0 seconds and 6 seconds, it is at rest. We want to find the distance it moves before it comes to instantaneous rest. To find the distance, we should note that this is a quadratic. The velocity equation is a quadratic, and we just found two roots. We look at the squared term of the quadratic, and it's 3 is in front, and so we know that that's positive, which makes it a smiley quadratic, which means the function is under the horizontal axis between 0 and 6. That's not a problem for us, and we can actually do the integration from 0 to 6 of the velocity, which is 3t squared minus 18t with respect to t. That's going to give us a negative answer. For the distance, we just make it a positive. So if we integrate t squared, we get t cubed. We divide 3 by 3, we get 1. And we integrate t, we get t squared. Divide 18 by 2, we get 9. And we're going from 0 to 6. So for the displacement, we are going to get 6 cubed minus 9 times 6 squared minus, it's just going to be 0 minus 0, which we put into a calculator and we find the displacement is negative 108 meters, but we realize that by considering the graph. Therefore, the distance, we have to make it positive because it asks for distance, not displacement. Distance traveled is just 108 meters. And we're done. So two particles of mass is 0.8 kilograms and 0.2 kilograms connected by a light, inextensible string that passes over a fixed smooth pulley. The system is released from rest with both particles 0.5, half a meter above the horizontal floor, see the diagram. In the subsequent motion, the 0.2 particle does not reach the pulley. Well, obviously the 0.2 kilograms is going to go up because 0.8 is heavier, so it's going to fall down. Show the magnitude of the acceleration is something and find the tension in the string. It's always nice that they give us an answer that we can work out. So we're going to create force equations for each mass. And so let's start with the 0.8 kilograms. What we know is the resultant force, which is mass times acceleration. And that's going to be 0.8 times acceleration, which we don't know, is equal to the force down, because the resultant force is going to be going down for the 0.8. And the force down is just the weight, which is 10 times 8. So 10 times 0.8, which is 8. And minus the force up, which is the tension. And we've done a force equation for the first one. For the second one, the 0.2 kilograms will be moving upwards, and so its resultant force will also be mass times acceleration. So it'll be 0.2 times A. And it's going to equal the tension, which is pulling upwards, minus the weight, which is going down. And weight is mass times gravity, and gravity is 10. So the weight going down is 2. All right, there are our two equations which we have to solve. Notice that one has a negative t, one has a positive t, so we can just add those two equations together. And we'll get 0.8a plus 0.2a is just 1a. We'll get t, negative t plus t is no t, and we have 8 minus 2, which is 6. And so we actually showed it very quickly that the acceleration is 6 meters per second squared. To find out the tension, pick any equation. Let's choose the second one. The tension is going to equal to 0.2 times the acceleration, and we'll take the 2 over, so then we're going to add 2. And so what we get for the tension is 0.2 times 6 is 1.2, plus 2 is going to be 3.2 newtons. All right, let's put our answers together, just so whoever's marking it can see them on the same line. Acceleration is 6. It's nice that it turned out to be 6 because they told us that it was 6. When the 0.8 kilogram particle reaches the floor, it comes to rest. Find the greatest height the 0.2 particle reaches above the floor. Okay, so the 0.8 hits the floor, it immediately stops. At that point, the 0.2 kilogram particle is traveling at the same velocity that the 0.8 had when it hit the floor, but it's going upwards. It's going to continue that with gravity affecting it until it comes to instantaneous rest where it starts to fall back down again. And we just have to work out the distance that it travels to find the height. Right, so first things first, we need to find the velocity that the 0.8 kilogram particle hits the floor with. It is constant acceleration, so we can use constant acceleration formulas. And what we know is that the initial velocity, the system started at rest, so the initial velocity is 0. The acceleration is not gravity because there is a weight stopping it from falling. We worked it out, well, they told us in the previous part, is going to be 6 meters per second squared. The distance that we travel is a half, because it's a half a meter above the ground, and we want to work out what the final velocity of this 0.8 kilogram object is. The formula that we use, it's on the formula sheet if you can't remember it. V squared is U squared plus 2AS. It's probably always a good idea to check so you make sure you get it right. U is 0, so that's kind of handy. So V is going to be the square root of 2 times A times S. Let's write it. 2 times 6 times 0.5. Well, a half of 2 is just 1. And so V is the square root of 6. All right, that's our final velocity. Let's leave it at that, as that for the moment. 6 meters per second. That tells us that the 0.2 particle, it has now traveled half a meter upwards because the 0.8 fell half a meter down. It's now a meter above the ground, and it is going to just function under the influence of gravity. And so what we know now is for the 0.2 particle, that the initial velocity is going to be square root of 6. The acceleration is now downwards. That velocity is upwards and acceleration is downwards, so we'll make it 10 because our initial velocity was positive and acceleration is in the opposite direction. The final velocity is when it comes to rest. It's going to be 0, and we're interested in, well, what's the distance? In this case, displacement, that it traveled. So we need a formula that uses VU, A, and S. It's the same formula again, but this time we're interested in S. Let's rearrange the formula. We're going to get S is equal to V squared minus U squared divided by 2A. All right, so for us, that means V squared is 0. So we're just going to have, all right, let's write it. 0 minus U squared, U is root 6. It's just going to become 6. Divided by 2A, and A is negative 10, so negative 20. So we have negative 6 over negative 20, which equals 0.3 meters. All right, our answer is going to be 1.3, which is the greatest height. Because if you remember, it started at half a meter above the ground, and it then traveled another half a meter while the 0.8 was pulling it downwards, and then we traveled 0.3 till it came to rest. That equals 1.3 meters. All right, question 6. A car of mass 1,500 kilograms is pulling a trailer of mass 750 kilograms up a straight hill of length 800 meters, inclined at an angle of inverse sine of 0.08 to the horizontal. All right, let's start making a diagram. Make this maybe a little easier to understand. There's our slope. Okay, so they told us something that maybe is a little unusual. The inverse sine of 0.8 is the angle, and so that's the angle. Let's sort this out. That means inverse sine is 0.8. That means sine of the angle is equal to 0.08. All right, so that's helpful for us maybe later on. We have a car and a trailer. I'm just going to use blocks, save time, right? And what we know is both of these are going to have a weight. And so the weight is going to go straight down, but the component of the weight which is acting against the vehicle is the weight which is going down the slope. Of course, we have the normal going into the slope. So the component down the slope is going to be the weight sine theta, and we know sine theta is 0.008. So that's where that comes in quite handy for us. The resistance of the car is 400 and the trailer is 200. So we're given forces, 400 newtons for the car and 200 newtons for the trailer. Okay, the kinetic energy is it loses kinetic energy because it has 30 meters per second at the bottom of the hill, and when it gets up to the top, it's now going at 20 meters per second. And the distance it traveled was 800 meters, right? 800 meters up the slope. Okay, we're told to use energy methods. I don't think I finished reading it. The car and trailer connected by a light rigid tow bar, so That's nice. The car and trailer have speed 30, 20 at the top. Use the energy method to find the constant driving force as the car and trailer travel up the hill. Okay, so what we know about energy is energy can't be created or destroyed. It can only just change the form. And the forms that we are dealing with are kinetic, potential, the resistance, and the driving force. And so the driving force is giving energy to the system. Potential is taking, because we're going up a hill, it needs to be given energy to actually go up. Kinetic energy is actually giving energy because it's losing the velocity. So it's handing energy out, and the resistance is taking energy, of course, because it's resisting the movement. So our energy equation will be the things that are giving energy, which is the driving force, say driving force, plus the kinetic energy is going to equal the resistance plus the potential energy. Resistance and potential are both taking, and the driving force and kinetic are both giving. All right, let's put this together. So work done is energy. The work done is force by distance. We're going to use that for the driving force. The driving force, because it's constant, over a distance of 800 meters is going to give us the energy on the engine. We don't know the force, but we do know the distance is 800. The kinetic energy is what we lost, and so we're going to take a half of mv squared, which in this case is going to be a half. All right, so what's the mass? It's the mass of the two combined items. So it's 1500 plus 750 is 2250 kilograms, and half mv squared times 30 squared minus a half 20 times 20 squared. All right, so that's what the kinetic energy gave, and that is going to equal the resistance, okay, plus the potential energy. All right, the resistance is, we've got two forces there, 200 and 400. And we are going to find the energy by force by distance again. And so we can do 200 times 800 plus 400 times 800, or we can just combine them and do 600 times 800 for the resistance. And the potential energy, this is where we're going to use the sine theta, is mgh. The mass is the mass of, again, both objects together. So that's going to be 2250 times gravity, which is 10, times the height. The height is that it traveled is vertical height, of course. And that's going to be 800 sine theta. So 800 and sine theta, we actually know they told us, is 0.08. All right, there's our awesome equation. Okay, so maybe we should simplify this just a little bit. We'll make it a little nicer to deal with. So we have 800 times what we're trying to find, the force, plus, if we put this into a calculator, a half 2250, and we can have in brackets 30 squared minus 20 squared gives us 562 500. And that is going to equal the other side, 600 times 800 plus 2250 times 10 times 800 times 0.08 is 1 million, no, 19, 123, 123. Okay, 1920000. All right, so our force, driving force, is going to equal 1920000 minus 562500, and then divide that by 800, and we get 1,696.875 newtons. Okay, the front of the paper says give your answer correct to 3 significant figures. So our driving force is going to be approximately, we're going to the 9. The 9 goes to a 10. 1700 newtons. Part A done. After reaching the top of the hill, the system consisting of a car and trailer travels along a straight level road. The driving force is the same. The resistance to motion are unchanged. What's the acceleration of the system and the tension in the tow bar? All right, so the diagram generally helps. That's almost straight. We have our car pulling our trailer, and we want to understand what's going on with the forces. I'm going to make the tow bar longer so we can see. There is a tension pulling backwards on the car. There is a driving force, which they tell us is 2400. There's a resistance which is unchanged, and that was 400 newtons. And what else is there? That's it. The resistance, the tension, and the driving force. For the trailer, there is, of course, the tension is pulling the trailer in the other direction, and there is a resistance of 200 newtons. All right, so to analyze what's going on here, we treat each part individually, and we say we want to find the acceleration. And so we know that there's going to be a resultant force. And we're going to make force equation for each part. Let's start with the trailer because it's easier, right? So the resultant force is mass times acceleration. The mass of the trailer is 750. So we have 750 times acceleration is equal to, okay, is it accelerating forwards or is it accelerating backwards? Let's just assume it's going to go forwards. So we'll say the tension is larger than the 200, and that's going to be the force of acceleration, or the resultant force. Yeah, of course, if we're wrong, A will be negative instead of positive. All right, so when we go to the car, we're going to do the same thing. We're going to have a resultant force, which is mass times acceleration. The car's mass was 1,500 times the acceleration is equal to the forces going forward, which is 2400, minus the forces going back, which is 400, and also we're going to subtract the tension. Okay, if we can, let's add those two equations together because we've got a negative t, we've got a positive t. If we add them, it's going to turn out very nicely for us. 1500 plus 750 is 2250 times the acceleration. The t's cancel out, and we get 2400 minus 400 minus 200, which is 1800. Which gives us an acceleration of, use your calculator, 0.8 meters per second. All right, to find the tension, we just go back to one of the equations. The first one seems easier, and we'll get the tension is equal to 750 times 0.8. Move the 200 over to the other side, and that gives us a value for the tension of 800 newtons. Let's put the two answers on the same line again. Tension is 800 newtons, and the acceleration is equal to 0.8 meters per second squared. Hey, I didn't write squares before. Let's fix that. No, that's good enough. Last question, 3 points. A, B, and C lie on a line of greater slope of a plane inclined at 30 degrees, with AB is 1, BC is also 1 meter, as shown. A particle of mass 0.2 is released from rest at A, slides down the plane. The part of the plane from A to B is smooth, tells you there's no friction, there's no resistance to the movement. The part of the plane from B to C is rough, which coefficient of friction mu between the plane and the particle. Given that mu is equal to root 3 on 2, find the speed of particle at c. This question needs to be broken into two parts. Let's find out what happens from A to B, what speed does it get to, and then the resistance or the friction is going to kick in and it's going to slow it down. And so we'll have to take that into account for the second part. So for the first part, all we need to do is find the force down the plane. Our particle is sitting on a plane at 30 degrees, and we want to know, well, what's the force, which is the component of the force going down the plane, N. So the weight of the particle, well, the mass is 0.2. All right, so the weight is 2, and the angle is 30, so the force down the plane is going to be, where should we write this? Force down the plane is going to equal the weight, sine of the angle, sine 30. Sine 30 is 1, and so the force down the plane is just going to be, sine 30 is not 1. Sine 30 is a half, and a half of 2 is 1, and so the force down the plane is just 1 Newton. All right, so we can find the acceleration from that because F equals ma. So the acceleration is the force divided by the mass, and the mass is 0.2. Which, of course, means our acceleration is 5 meters per second squared. Okay, it's going to be a constant acceleration because the force is constant, and we can then use constant acceleration formulas. What we know is it started at rest, so the initial velocity is 0, the acceleration is 5, the distance it travels is 1 meter, and we would like to know what its final velocity is, because that's going to be the initial velocity of the second stage. The formula we use, v squared, is u squared plus 2as. And so v squared is going to equal 0 plus 2 times 5 times 1. 2 5s are 10, so which tells us that v is square root of 10 meters per second when it reaches E. For the second stage of the journey, the force down the plane is going to be the same because it's just the weight, so it's still going to be 1 Newton. But now we have friction, which is going up the plane, and so the overall force is going to be those two forces added together. All right, so we know that the friction is the coefficient of friction times the normal, and the coefficient of friction we were told is root 3 on 2, and the normal we can work out, which is going to be the mass times cos of the angle, cos of 30. Cos of 30 is root 3 on 2, so we're just going to end up with the 2, and the 2 times root 3 on 2 just turns into root 3. So we have root 3 times root 3 on 2, which is just 3 on 2 newtons. 3 on 2, which is 1.5 newtons up. So what that tells me is the resultant force is going up the slope, because we have 1.5 going up, we have 1 going down, and so the resultant force is 0.5. All right, let's write it. 1.5 newtons going up minus 1 newton going down is 0.5 newtons up the slope. So it's decelerating at this point. Okay, so what we know is its initial velocity was root 10. We worked that out from the previous part. The acceleration, oh, we haven't done the acceleration. The acceleration is the force divided by the mass. So it's going to be a half divided by 0.2. And the distance that it travels is 1, and we want to know what is the final velocity. Right, so 0.5 divided by 0.2 is 2.5. Keep that in mind. Right, what formula we're going to use? V squared is u squared plus 2as. same formula again. Oh, final velocity, that's what we want. V squared is u squared. All right, let's write the formula. Plus 2as. So in this case, it equals u is root 10, so u squared is just 10. We're going to add 2, but acceleration is negative because it's against the direction. So let's multiply by negative 2.5, and the distance we travel is just 1 meter. And so v is the square root of whatever that is. Oh, that's not hard to work out. 2 times 2.5 is just 5, so it's 10 minus 5. So v is the square root of 5, which is approximately 2.24 meters per second. All right, so that's the velocity when we reach c. Okay, puppy, given instead the particle comes to rest at c, find the exact value of mu, which is the coefficient of friction. All right, we can just work backwards on this problem. So the first part where it's going down the smooth part of the ramp is just going to be exactly the same. But the second part now, the friction needs to be higher so that it actually stops it when it gets to C. Okay, so let's work backwards. We know that at B, the initial velocity is root 10. What we want to happen is the final velocity, that doesn't look like a B. The final velocity needs to be 0, and we know the distance, the displacement is 1 meter. And we would like to know, well, what's the acceleration that is going to cause that? Of course, that acceleration is going to be negative because it's stopping the object. V squared is u squared plus 2as. It's the formula that we're using again. But we're trying to find the a. So a is v squared minus u squared. V is 0, so let's just write u squared is 10. Oh, u is 10. U squared is 10. But we're subtracting it from 0. Okay, I'll write it all. 0 minus 10 divided by 2 times s, which is just 2. Oh, well, that turns out nice, doesn't it? The acceleration is negative 5 meters per second squared. And of course, it's negative because the acceleration is up the ramp. Okay, so that's our resultant force, which is going to be mass times acceleration. We know the mass is 0.2 times the acceleration. Let's make the acceleration positive and just remember that it's going up the ramp. Is going to equal the force which was going up the ramp, which is the friction, minus the force going down the ramp, which is we worked out before, it's just 1 Newton due to the weight. 0.2 times 5 is just 1, and so we have, what do we have here? We have 1 is F minus 1. Oh, so the force of friction is equal to 2 newtons. Okay, and we know that the force of the friction is equal to mu times the normal. The normal is the weight, which is 2 times cos of 30. So we're going to have the coefficient of friction is 2 divided by 2 is just 1. So 1 over cos 30. Cos 30 is root 3 on 2, so mu is going to be 2 on root 3. All right. We can leave mu as 2 on root 3, or we can rationalize rationalize the denominator by multiplying by root 3 on root 3, which will give us 2 root 3 over 3. I don't know, either will be fine, I think. And that's the end of the exam.